Okay, now we're going to dive into friction. It's a little bit mysterious, this thing called friction. You're rubbing your hands together, and there's a little bit of a resistance. What's that about? My hands are pretty smooth, right? And if I rub them together really fast, they get hot. What's that all about? Right? Well, in order to understand this, you have to take a little bit of a closer look at what surfaces look like on at a very microscopic level. Okay? So in our exploration of friction, okay, we're going to look at two surfaces, and we're going to like zoom in with a microscope, okay? And we're going to notice that if I have like two smooth surfaces rubbing against each other, if I zoom in, the surfaces are not smooth, right? This isn't actually this. This is an illusion. This smoothness of my hands rubbing together, that's also an illusion, because when you get right down to it, there is all this going on, right? So there's all these little mini normal forces, right, when these surfaces are colliding with each other, okay? One thing that I like to point out is that if, just to kind of like represent how things that look really smooth can actually be really, really rough, if you were to take the Earth, okay, with all its mountains and its Everests and its like deep trenches in the oceans, right? And you were to shrink it all down to about the size of my fist, okay? It would be smoother than a cue ball, okay? That just goes to show you how rough a surface can look like that looks entirely smooth if you actually like really kind of zoom in, okay? So it's an anecdote for you. So this is what's actually happening, and that is why, I can have my coffee cup here, and I can apply a force, and it doesn't tip over right away, it doesn't slide right away, because this surface and this surface are actually kind of rough like this, and there's going to be some resistance, and that resistance is called friction, okay? So if you guys could advance to the next slide that talks about static friction, okay? So let's suppose that I have a box on a table, okay? And let's suppose that I decide that I want to start pushing it, right? But before I start pushing it, I want to acknowledge that there is just a normal force going up, and then there's a weight going down, okay? That's all that exists. But I want to add to that a small little force of F, okay? Okay, so I'm adding that guy, right? Now, when I add this guy, the second that I add this guy, there's these little interactions happening down here between that box and the surface, okay? And so immediately, he's going to start pushing back with a little frictional force. We'll call it static friction, okay? And I'm calling it static friction because it's not moving yet, right? You guys know that there's like this thing that happens where like you can push on something, but at first it doesn't move. You have to push quite a while before it actually starts to accelerate, okay? All right, so but I'm pushing on it and it's not moving yet, right? That's because the second I push on it, I have a frictional force pushing back that matches that force. It's not going to exceed it. It's not like it's going to suddenly like be really huge and so like I push this way and I fly back, right? Okay, it just meets it. And I can go ahead and push a little bit harder. Here I go pushing harder, right? And this guy will push harder back. He's going to meet me. He's going to meet me, right? But all of you know that there is some point where I'm pushing, but at some point it can't meet me anymore, and the force that I push with overwhelms static friction, okay? So that maximum friction at which he cannot exceed, right, where he can no longer meet the force that I'm applying, okay, that static friction is given by the formula Fs equals this thing called mu s, right, times the normal force. On the slide here it says Fn, but I just like n for normal force, so you can use either one that you're comfortable with, okay? So this mu(s) is called the coefficient of friction, and it basically is this little coefficient that determines like the roughness of the surface, right? So there's a different mu for every two different surfaces. They have their own little like mojo, their own little vibe together, right? So for any two surfaces, there will be some mu, and this coefficient is not always, but it's usually between 0 and 1, okay? It doesn't have to be, but you'll see most of the values you get are in that range, okay? So just to remind you one more time, this frictional force, the static frictional force, will keep pushing back, pushing back, pushing back, will resist the force that I'm pushing until it reaches this maximum value, you know, whatever n is. In this case, n is going to be just equal to the weight, right? All right, and so yeah, that n times the coefficient of friction, whatever that is between these two surfaces, right? So when this force here that I'm pushing reaches this value, right, then it can't resist anymore. And if I do it any stronger, if I raise my force any bit above that, if I start pushing any harder, it will overwhelm this force, and I will start to get an acceleration in this direction, okay? Now, the second you get that acceleration, the second it starts to move, then click. The static friction goes away, and advance to the next slide, you have something called kinetic friction, okay? So as soon as this is big enough, right, right, and this actually starts to accelerate, then now this turns into kinetic friction, which is a little bit different, right? The force of kinetic friction is, I'll write it over here, is actually equal to mu k times n. And mu k is typically less than mu s, okay? The coefficient of kinetic friction is less than the coefficient of static friction, and everyone kind of understands this intuitively, right? You guys kind of have this kind of vibe that it can be hard to start to get something moving, right? But then once it gets moving, it's easier, right? And so you guys can see that with this, there's this little graph where it's like, you know, as I'm increasing my force, then there's this drop because the coefficient of kinetic friction drops from mu(s) to mu k. Okay, so the big takeaway here, right, is that once you're moving, the force of friction is a little bit lower. Okay, and that once you're moving, there will always be some resistive force existing because of this roughness between these two surfaces. Okay, now. So far in this course, we've idealized this, and we've said, the hell with you, friction, okay? And we pretended it doesn't exist, right? In this chapter, for the rest of this chapter, we're going to pretend, well, we're going to stop pretending, right? Friction exists, and it doesn't matter what the situation is. Let's say this is like some kind of like a plane, and I have a box on it, right? And let's say it starts to slide down in this direction, right? By, you know, some component of gravity, the x component of gravity here. Right? There's always going to be some kinetical friction force, right, opposing it. And if it's not moving, that kinetic frictional force will actually be static frictional force. Okay? That's what I want you to take away from this. That is the foundation that I'm laying before we move into actually solving these problems, okay, with friction. And I'm going to start with a very interesting question. It's a true story about these mysterious rocks in Death Valley. I'll see you there.